here to talk to us about visionary space elevator architectures. Peter Swan is president of the International Space Elevator Consortium, and he's led a team to further concepts of incremental studies and yearly conferences, and over the last 10 years, he's published 8 books as co-author and co-editor. He has a history and graduated from the U.S. Military Academy in 1968 with a Bachelor of Sciences and served 20 years in the Air Force with a variety of research and development positions in space. He's worked on the Iridium concept with Motorola, and he's here to talk to us about visionary space architectures, and I will let him take it away.
Okay, thank you. Okay, good morning. I am really excited about being here, and 7 minutes is definitely a challenge. So I'll shoot for 5 and see how that works. Okay, the space elevator is going to provide a breakout technology which will impact humanity. But first, let's talk about the elephant in the room: carbon nanotubes. There are 2 realities that are staring us in the face. The first is we cannot build a space elevator today without a material that's strength-to-weight ratio is about 1,000 times better than steel. We're well short of that in a manufacturing sense. The second point is that there's material in the laboratory that can do it. They've grown carbon nanotubes to 10 centimeters, and they've in excess of 150 gigapascals. Those are sufficient numbers for our system. Dr. Mark Haas, who's going to be talking this afternoon at 4 o'clock in the space elevator track, will be talking about this particular problem. He's estimated that there will be sufficient material with the strength and the length characteristics close to 100% defect-free by the 1930 to 35 time period. 2030. Yeah, now I'm dating myself. Anyway, his prediction is that we will have a material sufficient for space elevators by the early 30s. Now the question is how? Once the tether material is manufactured, the execution of the space elevator program will be linear, reasonable, and a known sequence of events. First, the tether will be placed in the geosynchronous location through the normal rocket capabilities. The tether will then be lowered to the surface of the ocean, and at the same time, the mass above the geosynchronous arc will be raised so that the center of mass stays where it's supposed to be. Once you've grabbed it on the surface of the ocean, then we would build up the mass of the tether by having small tether climbers and moving up and adding mass. Now, we have a few little problems we're working on, like we have no flipping idea what the coefficient of friction is on carbon nanotubes. So, how do you grip it? All those little problems that we're working on. But as the business world embraces the space elevator infrastructure, missions will increase. And as the missions increase, then the mass flow upward will be remarkable. After a few years of operations and continued build up the system, we'll then add human capability for a full operational capability, probably by 2050, something like that. It's important to remember that one of the first functions we have to do is build the second space elevator and the third, because we don't ever want to get trapped by the tyranny of gravity again. Concerns. Of course, there are many areas of concern, and our study team is pursuing them. The International Space Elevator Consortium, along with the Japanese Space Elevator Association, are taking on the individual challenges and trying to understand their impact in their proposed engineering paths to lower the risk. Let's go to the next one. The ISAC has produced 5 individual reports, and we're currently doing 3 studies that will complement those different questions that we've laid out proposed answers for. Each of the 1-year-long studies proposes engineering and programmatic solutions to some space elevator risk. Some topics there are space debris and the atmosphere that we have to go through. So we continually take on the issues of concern and systematically lay out the engineering processes that we can leverage for success. The hope. It turns out the community of the Space Elevator enjoys the challenges, and we aggressively approach the development of the transportation system in a seasoned and mature approach. We have done major system development before. Panama Canal, transcontinental railroads, the interstate highway system, the aviation industry serving the globe, and of course, walking on the moon. Space elevator development will be a mega project. However, from my perspective, it seems to be a three-step process. Step one, prepare for the project by incrementally increasing the body of knowledge. Step two, develop the material towards thousands of kilometers in length with the proper characteristics. Both of those are going on in parallel. Step three is then initiate the full program for 3 space elevators, enabling the breakout from the Earth's gravity. The conclusion that the International Space Elevator Consortium has is we can accomplish this huge challenge, which will lead humanity off planet into the next frontier. Thank you.